Today we are going to consider filter design, and we are going to explain where is this coming from. So we are interested in the filter design, and we are going to give examples of and how we generate essential features of the filter. So let us look at the following simple example that we have a chemical or other type of the reactor that flow is coming in, tank in other words, and since we are measuring here, so measuring, I will put the m, the height, we essentially take this signal, this measurement signal, and we want to put this measurement signal on the screen. However, since we have a high frequencies here, I will put the yellow, the high frequencies and oscillations in this surface of the tank. We don't want that these high frequencies of the flow generated by the flow coming in to show up in the on the monitor as a evolution of the tank height. So in other words, if I have a monitor here, I don't want these high frequencies to show up ever on the screen. I want to smooth that out. And one way to smooth it out these high frequencies is to apply the filter. In other words, we can have a filter here. How do we know that? We know that every function can be decomposed as a f of x can be represented as a function that is decomposed in sine x. So it goes from 0. It's a Fourier series, sine and cosine. So in other words, all these high frequencies are nothing but the high frequencies that we have, and we can describe these high frequencies with any of these functions. So there are here coefficients a, n, and here there are coefficients b, n. Okay, so any function, essentially these high frequencies can be decomposed in this, and if we have any of these high frequencies, in other words, if this is the signal, that is measured, we want to smooth out that signal by removing these high frequencies. So it has to be something like this. Okay, so we understand what we want to do and how this is related to the previously what we learned. It is that we already learned a very interesting feature of the linear system, that if we have a sequence A of k that is given as a of k, and we apply to the linear system, then if this A, G of Z, if this is A, it's a characteristic of G of Z, and its characteristic as a zero of this transfer function, we will have a zero output here. In other words, if G of A is equal to 0, this linear system becomes filtered. And that's very interesting because why? We can build a filter for every signal, essentially, that we want to filter and block. In other words, if for the previous model we have simple control now scheme, that here we have a measurement and then if we don't have a filter, we will have it directly into the controller feedback, and we will feedback this into the height controller, which is this valve. In other words, if this height changes, measurement device records that and sends to the simple feedback mechanism that opens and closes this valve to regulate the height of this. In other words, if the height is some reference point, from dynamical model of the system, which is G of Z, we obtain the measurement, and this can be written as follows. Now, if we realize that due to this oscillation of the height here, we will have also essentially signal that will oscillate, and it will be amplified by this simple controller, and will amplify this actuator that is valve. We want to remove it, and what do? We will essentially add here in this part so we will just cut it here and we will add a filter. We guarantee that we don't have a filter here. So we guarantee that we will not have a certain signal in a closed loop. So what does it mean? Let's say that the tank process is described as a G of Z as Z minus 0.2, and that we want to filter to block. Filter blocks the sequence this is desired sequence that we want to filter or block. .5. In other words, we know what is the Z transform of this sequence, and we have that this is just a Z minus 0.5. Okay, so if we don't want to have this sequence, we'll just invert the transfer function of this signal. So G of filter is going to be just -1. In other words, G of filter is going to be Z minus 0.5 divided by Z. We just invert it, because if we have that this is inverted, when U multiplies this term, Z minus 0.5 and Z minus 0.5 from the signal will cancel out. Therefore, having this object here, any signal here, U of K, that is of the type 0.5K. When it goes to here, it will encounter filter here, and since filter has a this transfer function, this is not going to be passed to the controller. How do we know that? Let's just write here what is the transfer function of this system. So we had R, we have a G of Z, this stays the same, and from the output now we have a filter here, G of filter. Okay, plus minus. And so now finally, when we look at the obtained system, we already know how to calculate the overall transfer function. So we are claiming that this big G of closed loop Z is going to be forward transfer function G of Z divided by 1 plus G of Z, everything what we pick up in the closed loop, G of filter of Z. Okay, and when we simplify this expression, we just have to ensure. Okay, let us write this. So the transfer function was Z divided by Z minus 0.2. Here we have a 1 plus the same Z minus 0.2, and here we have a Z minus 0.5. Okay, this term and this term gets cancelled, this term and this term gets cancelled, so that we obtain the following: G closed loop of Z is equal, so becomes Z 2Z minus 0.7, if I'm not mistaken. So finally, we need to ensure that when we build this filter here, as it is given in this expression, that the closed loop system is still stable, that we do not destabilize the filter. And is it stable? We will see that Z 2Z minus 0.7 is stable as well. Okay, so therefore this is the way how to construct the filter that is going to block any high frequency signal, and in this case the signal is going to be 0.5 K in the closed loop, so we will not see that, because if we have any disturbance that is coming here, for example, and this disturbance is this equals 0.5 K signal, this will be eliminated due to the feature that this filter, essentially, when it's evaluated, it's inverse transfer function of this signal, and therefore it will cancel. So this is pretty much the essence of the lecture on the filter design.